A recent paper published in ACS Sustainable Chemistry and Engineering describes the development of an amine functionalized pillar-layered metal organic framework, APMOF cobalt, that has the ability to produce high purity methane from a natural gas mixture containing 5 different components, butane, propane, ethane, carbon dioxide, and the desired product methane. The efficacy of this newly developed APMOF cobalt is established on the basis of measurements of unary isotherms and transient breakthrough experiments and transient breakthrough simulations. The paper reports data on the unary isotherms for each of the 5 components in the natural gas mixture at 3 different temperatures: 273 Kelvin, 298 Kelvin, and 313 Kelvin. At each temperature, a total of 250 data points are reported for each gas molecule. What is interesting about this paper is that the isosteric heats of absorption of butane, propane, ethane, carbon dioxide, and methane have been reported with inclusion of error bars in QST calculations. As far as I am aware, error bars in QST calculations are not commonly reported in the MOF literature. I explain in this video presentation how these error bars in the QST calculations are calculated. The unary isotherm data for each of the 5 components is fitted with the dual-site Langmuir-Freundlich model with temperature-dependent parameters, as is described in earlier video presentations of mine that are listed here. The fitted parameters for each of the 5 components in the natural gas mixture are provided in this table, and as an example I show the comparison between experimental data points for propane. Red circles are the experimental data at 273 Kelvin. The green squares are for 298 Kelvin, and the blue triangles are for 313 Kelvin. The DSLF parameters for each guest, say for butane and propane, requires the fitting of 4 different parameters, and these parameters are determined simultaneously by regressing all available data points at the 3 different temperatures. The number of data points is about 250 for each gas molecule. The fitting is performed using the Excel solver. The accuracy of the fitting of the unary isotherms is quantified in this paper by data on two parameters, r squared and sigma, that are tabulated in the supporting information accompanying this paper. The r squared values may be calculated using the RSQ function in Excel, that is an inbuilt function. Basically, you prepare a column of values of experimental unary isotherm data points and the values of the corresponding DSLF fits, and by choosing and selecting columns M and N for the experiments and the fitted parameters, you can calculate the r squared values using Excel. In addition, you can determine the fractional error from this formula, where the experimental data points and its deviation from the DSLF fits are analyzed to calculate a value of sigma that represents a fractional error. N is the total number of data points, and there are 250 data points for say each of the guest molecules listed here. Further details on these calculation procedures are described in the supporting information accompanying this paper. From the DSLF fits, the isosteric heats of adsorption may be calculated using the Clausius-Clapeyron equation. As I have described in earlier video presentations of mine that are listed here, the calculations of QST can be performed analytically for the DSLF fits. Now, the source of error in the QST calculations is entirely due to errors in the estimation of the loadings using the DSLF fits, and these errors are quantified by the parameter sigma that I have explained in my previous slide. This is the fractional error in the calculations of the loadings that are calculable for each of the guest molecules. Therefore, the error bars on the QST calculations are calculated by this expression, QST plus minus sigma, which is a fractional error, times QST. So the errors in the unary isotherm data fits gets directly reflected in the errors in the estimation of the QST.